Welcome to lecture 3 that will be on the principle of induction. So, what does the principle of induction says? The principle of induction can be stated as follows. Let P of n be a predicate with parameter n b being a natural number, so an element of the set 0, 1, 2, and so on and so forth. Now, let's suppose that first P of 0, which is basically the predicate evaluated when n is equal to 0, is true. Let's then also suppose that if for every n in the natural numbers, P of n, so if the predicate evaluated at n is true, when that would imply that P of n plus 1 is true. Okay? So if these two statements are true, then we can conclude that P of n is true for every natural numbers n. So basically the principle of induction is a way of proving that a predicate is true for every possible n, so which would be just like proving infinitely many possible statements. But instead of proving infinite many possible statements, we just prove two. We just prove the first one, which is called the base step, which basically consists in evaluating the predicate at n equals 0 and checking that this is true, and then proving the induction step. So the principle of induction basically gives an operative procedure for proving P of n for every n. So the first step would be put n equals 0 and check that P of 0 is true. Second, assume that P of n is true for a generic n, and prove the following implication, that P of n implies P of n plus 1. Now, if 1 and 2 succeed, we can then conclude that P of n is true for any natural numbers n. Now, rather than giving a formal proof of this principle, we'll just give an intuition of why this works. And the intuition is the following. So in the first step, we basically prove that P of 0 is true, okay, by the first, right? So by the first. Then, assuming that P of 0 is true, we can conclude that P of 0 would imply P of 1, and this is by the inductive step. But then, if P of 1 is true, we can say that P of 1 implies P of 2, again by the inductive step. and so on and so forth. So in a way, this is just like having a line of dominoes, and basically the first step, the base step, is basically equivalent to say that the zero domino falls, and the inductive step is just like saying that if the n domino falls, then the n plus 1 domino falls. There is an interesting variant to the principle of induction, which is the following. So if the base step is verified for, let's say, n equal to 1000, which is to say that p of 1000 is true, then p of n is true only for n larger than 1000, and this is completely understandable, because if just the domino number 1000 falls, only the dominoes that follow 1000, which is 1001, 1002, and so on and so forth, will fall down. Right. Okay, so we can use the principle of induction for proving, okay, as an example of application. We will prove some equalities with the principle of induction. Okay, and the equalities that we will prove are the following. Let's say the first one will be this one: the sum of k, for k that goes from 0 to n, which is to say basically 0 plus 1 plus 2 up to n. So the sum of the first n natural numbers is given by this formula: n times n plus 1 divided by 2. So this is the first equality that we would like to prove with the principle of induction. The second equality is that the sum k goes from 0 to n of k squared, which means 0 plus 1 plus 4 plus n squared, which is the sum of the first n squares, is equal to n times n plus 1 times 2n plus 1 divided by 6. And the third equality that we would like to prove is that the sum k goes from 0 to n of a to the k, so that means basically 1 plus a squared plus a to the n is equal to a to the n plus 1 minus 1 divided by a minus 1, provided that a is different from 1. Okay, so we want to prove these equalities just to show what is the power of the principle of induction. So let's start with the first equality. So the first equality is this: sum for k that goes from 0 to n of k, which is the sum of the first n natural numbers, is equal to n times n plus 1 divided by 2. So how can we, well, this is basically our predicate, p of n. We are predicating something with a single parameter n. In fact, this expression this expression can be seen as a single predicate, which is a function of n, and we would like to prove this. Okay, let's give the proof by the principle of induction. And remember that the proof by the principle of induction is structured in two steps. The base step would be to prove that P of 0 is true. But what is P of 0? Well, P of 0 is just the fact that the sum k goes from 0 to 0 of k should be equal to 0 times 1 divided by 2. But this is certainly true. In fact, the left-hand side is just 0 and the right-hand side is 0. So this is proved. Okay, so let's move to the inductive step now. So we want to prove now that P of n implies P of n plus 1. And P of n is the sum. K goes from 0 to n of k. This must be, well, this is just P of n equal to n times n plus 1 divided by 2. Okay, this being P of n. Well, this should imply that the sum k goes from 0 to n plus 1 of k should be equal to n plus 1 times n plus 2 divided by 2. And this is P of n plus 1. So remember that we will be now assuming that P of n is true, and we would like to prove that this implication holds. So the usual way for doing this is starting to evaluate the left-hand side Pn plus 1, starting from the left-hand side of Pn plus 1. So because we know we are assuming that P of n is true, we can write the sum for k that goes from 0 to n plus 1 of k. We can write this as just the sum k goes from 0 to n of k plus n plus 1. But now, by the assumption that P of n is true, we can rewrite the first term as n times n plus 1 divided by 2 plus n plus 1. And if we develop this, what we get? We get 2 n times n plus 1 plus 2 times n plus 1. Okay. So let's now develop the product at the numerator. We have n to the square, well, or we just now we can factor out this element, this term and this term, and we get n plus 1 times n plus 2, which is exactly what we were looking for. Okay, so we have now the complete proof by induction of the given equality. Okay, so let's move now to the second equality. The second equality was this: the sum k goes from 0 to n of k squared, which is the sum of the first n squares, equal to n times n plus 1 times 2n plus 1 divided by 6. Okay, and let's now give the proof by using the principle of induction. Remember that the base step would be just to prove that P of 0 is true. But what is P of 0 here? Is just the fact that the sum from k that goes from 0 to 0 of k squared, that should be equal to 0 times 1 times 1 divided by 6. But of course this is verified because on the left hand side we get 0, on the right hand side we get 0, so yes, this is done. Inductive step now. P of n should imply P of n plus 1. Now, what is P of n? Well, P of n, we assume that P of n is true, which is to say we assume that the sum k goes from 0 to n of k squared is equal to n times n plus 1 times 2 n plus 1, all divided by 6. And from this, right, so this is our p of n that we assume to be true. And from this we should prove p of n plus 1. So what is p of n plus 1? Would be that the sum k goes from 0 to n plus 1 of k squared should be given by n plus 1 times n plus 2 times 2n plus 1 plus 1, okay, all divided by 6. And once again, assuming that p of n is true, let's start by evaluating, just as we did in the previous example, let's start by evaluating the left-hand side of pn plus 1. Right, so we write sum k goes from 0 to n plus 1 of k squared. This can be written as the sum of k from 0 to n of k squared plus n plus 1 to the square. As you see, this is a recurrent approach for solving, for proving the inductive step, because what I'll try to do now is always try to extract this term, which is something that is given by the hypothesis of the induction step. And in fact, once again, we can replace to the first term the expression given by p of n, which is n times n plus 1 times 2n plus 1 divided by 6 plus n plus 1 to the square. Good. Okay, so a little bit of calculation now. So we can write this as n plus 1, 2n plus 1 plus 6 times n plus 1 to the square. And we can factor out n plus 1 here. So we are left with n times 2n plus 1 plus 6 times n plus 1, which is n plus 1 times, if we develop all the calculation, what we get? 2n squared. We get 1n and then 6n, so we get 7n plus 6. Now, what we would like to prove now is that this trinomial would be exactly equal to this trinomial, right? Because in fact, we already have this term, which is n plus 1, which already came out, okay? The 6 is okay, because the 6 is okay. So the only thing we would like to prove is that we would like this. We would like that this trinomial would be equal to n plus 2 times 2 times n plus 1 plus 1. Or if you like, this is just like saying n plus 2 times 2n plus 3. How can we prove this? Well, one way would be, because we already know where we want to get, so we can divide 2n squared plus 7n plus 6 by n plus 2. And if we do this division, we get 2n, which now will give minus 2n squared, and minus 4n, which will return 3n plus 6, and this will give another term in the quotient, which will be exactly 3, and in fact we get minus 3n minus 6. So yes, we can say that this is equal to n plus 1 times n plus 2 times 2n plus 3 divided by 6, which is exactly what we were trying to prove. So second equality also proved. Let's move now to the last equality that we wanted to prove, the third one. Okay? Third equality is that the sum k goes from 0 to n of a to the k is equal to 1 plus a squared plus dot 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 a to the n. And we want to prove that this is equal to a to the n plus 1 minus 1 divided by a minus 1, provided that a is different from 1. Of course, otherwise this doesn't make any sense, right? Good. Proof by principle of induction. Base step, p of 0. What is p of 0? Well, p of 0 is just like saying sum k goes from 0 to 0 of a to the k should be equal to a to the 1 minus 1 divided by a minus 1. But of course on the left hand side this is just 1, on the right hand side is 1, so this is proved. Inductive step. We want to prove that p of n implies p of n plus 1. But p of n is that sum k goes from 0 to n of a to the k is equal to a n plus 1 minus 1 divided by a minus 1. And remember that this is p of n. And from this we would like to deduce p of n plus 1, which is sum k goes from 0 to n plus 1 of a to the k is equal to a to the n plus 2 minus 1 divided by a minus 1. Of course, always in the assumption that a is different from 1. Good? Okay, once again, we will follow the usual procedure. We will start by evaluating the left-hand side of Pn plus 1 and see if we get what we were looking for. The sum k goes from 0 to n plus 1 of a to the k can be written as sum k goes from 0 to n of a to the k, usual step, plus a to the n plus 1. But by the hypothesis of the induction step, we know that this can be written as a to the n plus 1 minus 1 divided by a minus 1 plus a to the n plus 1. And this is equal to a minus 1 at the denominator. We have a to the n plus 1 on top minus 1, plus we have a to the n plus 1 that multiplies a minus 1. Okay, this is equal to a minus 1, and we have a to the n plus 1 minus 1 plus a to the n plus 2 minus a to the n plus 1. But notice that clearly this and this will cancel out, and we are then left with a to the n plus 2 minus 1 divided by a minus 1, which is exactly what we were looking for. As a second example of application of the principle of induction, let's apply the principle of induction to some inequalities. For example, let's suppose that we want to determine the natural numbers n such that the following inequality holds: 3 to the n is larger than or equal to n to the square. Right, so let's do a little bit of exploration first before moving to the general proof. Okay, so let's see what happens if n is equal to 0, because we might find out that this is never true, right? So if n is equal to 0, what we get: 3 to the 0 is larger than or equal to 0 to the square. Yes, this is definitely true because 1 is larger than or equal to 0. Okay. N equal 1. 3 to the 1 is larger than or equal to 1 to the square. Well, this is true as well. N equal 2. That means 3 to the square is larger than or equal to 2 to the square, and this is definitely true. Let's prove another one. Let's try another one. N equal 3. 3 to the 3 is larger than or equal to 3 to the square. This is true. So it seems reasonable to make a conjecture, and this is the conjecture, that it is true for every n into the natural numbers. But of course this is something that we need to prove, right? So let's start our proof by the principle of induction. So the base step would be p of 0, which in our situation is 3 to the 0 should be larger than or equal to 0 to the square, which is certainly verified, yes. Induction step. We should prove that p of n implies p of n plus 1, which is to say that if 3 to the n is larger than or equal to n to the square, and of course this is p of n, well, from this should follow that p of n plus 1 is true. So we should prove that from this follows that 3 to the n plus 1 is larger than or equal n plus 1 to the square. Right. Okay, how can we prove this? As always, we'll start from the left-hand side of Pn plus 1. So we have that 3 to the n plus 1, well, this is equal to 3 times 3 to the n. But by the hypothesis of the induction step, we know that this would be larger than or equal of 3 to the n squared. Okay? And now we would like to have that this would be larger than or equal of n plus 1 to the square. So let's say that this is our hope. Okay? We would hope to prove that 3 to the n squared is larger than or equal n plus 1 to the square. Okay, so let's make a check that this is indeed true. Okay, we would like to prove that 3n squared is larger than or equal of n plus 1 to the square. How can we prove this? Well, this is just like saying 3 to the n squared is larger than or equal of n squared plus 2n plus 1, which means that 2n to the square minus 2n minus 1 is larger than or equal to 0. And this is an inequality of the second degree, so we know that we need to find basically the roots of the corresponding equation. So the corresponding equation is 2 to the n squared minus 2n minus 1 equals 0, which gives basically the roots n equal to 2 plus or minus 12, which, I mean, by simplifying, we get 1 plus or minus square root of 3 divided by 2. So we know that if we have here 1 minus square root of 3 divided by 2, and we have here 1 plus square root of 3 divided by 2, so the let's say for these two values the trinomial is equal to 0. If instead we stay on the left, the trinomial is positive, on the right this trinomial is positive, and in between the trinomial is negative. So Apparently, a possible solution would be to take basically n less than or equal to 1 minus square root of 3 divided by 2, and n to the right of 1 plus square root of 3 divided by 2. But since square root of 3 is about 1.7, clearly we see that this solution cannot be accepted, right? Because that would imply that n would be negative, but we are just considering natural numbers. So the only possible solution for us would be exactly this. So n larger than or equal 1 plus square root of 3 divided by 2, which of course implies that this inequality is true for n larger than or equal to 2. So this was just a simple application of the principle of induction to prove an inequality. But there is a particularly important inequality that we would like to consider, which is the Bernoulli inequality. This is very powerful, and we will be using this inequality many times. So the Bernoulli's inequality is the following: 1 plus x to the n is larger than or equal 1 plus nx. And this is true for every n into the natural numbers and for every x larger than minus 1. So why it is this inequality so important? Because if you look at this, our p of n, right? So this is basically our p of n, the predicate evaluated at generic natural number n. It is transforming some a power of a binomial, which is always difficult to evaluate, because for any possible number n, we need to evaluate this power of this binomial 1 plus x into just a polynomial, which turns out to be very useful in calculations. Okay, so let's try to prove the Bernoulli inequality by applying the principle of induction. So this is the proof. Base step is p of 0, but what is p of 0 would be 1 plus x to the 0 should be larger than or equal 1 plus 0 times x. But clearly this is true because on the left hand side we have 1, on the right hand side we have 1, so yes, this is indeed true. Right, let's move to the inductive step now. We need to prove that p of n implies p of n plus 1. So p of n is that 1 plus x to the n is larger than or equal of 1 plus nx, and from this it should follow that 1 plus x to the n plus 1 is larger than or equal of 1 plus n plus 1 times x. So again, this is p of n, and this is p of n plus 1. Okay, so usual approach, will start from the left hand side of pn plus 1, and we can work on that. So we can write 1 plus x to the n plus 1, well, we know that this is just 1 plus x, times 1 plus x to the n, which is larger than or equal of 1 plus x times 1 plus nx. And we can say this just because of the hypothesis that, remember the hypothesis that x is larger than minus 1. So in other words, we say that x plus 1 is larger than 0. So we can multiply both terms of the inequality by a positive number and the inequality remains. So now we just need to develop this product, okay? So what we have, this is equal to 1 plus nx plus x plus nx to the square, which is 1 plus n plus 1 x plus nx squared. So the question is this something which is larger than 1 plus n plus 1 times x, which is exactly what we were looking for, remember, right? So we would say that this basically is the right hand side of the inequality. But this is definitely true because, yes, because n x squared is always larger than 0, right? So clearly, if we remove this element n of x squared, we clearly get something which is smaller. So this proves the inductive step of the Bernoulli inequality.